So what I would like to talk about is, and I have seen that there is a small portion in John's notes on character theory. And I will use the same notation as he used with one or two exceptions. So what we have here is a group G, which is either finite or a compact Lie group. And we have a mapping, rho tilde, as he wrote, from G into GL. And now this is supposed to be the dimension, and for today's talk I will use C there. So we use complex representations, and most of the theory is much more elegant if you do it in C, and many results carry over to R, but it's always a little bit tricky. So it's like if you talk about series of polynomials, then you would like to talk about C, because you have the fundamental theorem of algebra and so things like this. And so here it's also easier to have it complex and maybe give an interpretation to the real situation in a separate step. So this is our representation, and the new feature is we write a chi of rho tilde. This is a mapping from G into the complex numbers, and we map G onto the trace of rho tilde of G. And this is called, this is a character, is called character corresponding to rho tilde. So let me start with a very trivial remark. If you have a sum of two representations, so if you have rho tilde is rho tilde is the sum of rho 1 tilde, rho 2 tilde, and I think this was introduced by John in one of his lectures, which is when you do the following, you write rho 1 here and rho 2 tilde here, and you have, I mean, in form of matrices, you just have blocks where you put the one representation on the one side and the other representation on the other side. Then the character of rho tilde is the character of rho 1 tilde plus the character of rho 2 tilde. And I think looking at this picture, this is quite clear. And maybe I should say a few sentences of what is the objective of what we are doing today. So you might ask several questions. We had the notion of irreducible representation, and one question could be, how many irreducible representations do we find for a given group? Suppose we have a finite group. Are there finitely many irreducible representations, or are there maybe infinitely many irreducible representations? And if there are finitely many, how do we find them? And the second question is, we are seeing here a procedure to construct a new representation from smaller representations by adding them. Can we do the opposite? Can we decompose a given representation in smaller pieces, and how do we do this? And how many of the smaller pieces will we find? So these are the issues which are hopefully answered at the end of this lecture. There is a similar construction if you do this here. then you have a dot here. But if you don't, if you're not happy with this procedure, you don't have to give an interpretation to it. But if you are familiar with it, so you just take it. So let me see.
Kronecker product that you mean by that?
This is tensor product.
Tensor product of matrices.
Tensor product of matrices, I mean pointwise, and so is a tensor product of representations. And in fact, if we want to discuss what I did in my lecture, it's a beginning seminar, or it's a meeting in the first week where I talked about Moline series. If we want to look at this a little bit deeper, then we need this as well. But for the moment being, let me leave it like this. So we introduce a very fancy notation. We write L2 of G is the set of all F from G into C, which are square integrable. And then, of course, this we know is a Hilbert space. And we have an inner product, which I denote by F1, F2 is in case of a finite group, I write it 1 over the order of G times the sum over the elements G in G F1 of G, F2 of G bar. So the traces are special functions on the group, and so they are elements, at least for a finite group or also for a compact Lie group, they are elements in this space L2 of G.
Sorry, Reiner, what is, so the G is just a group, what is the measure with which you're integrating with respect to?
I mean here, if I have a finite group, I just do addition.
Okay.
So this is counting measure, and so this is why I normalized it by dividing by the number of elements in G, and if you have a compact Lie group like SO3, you take the Haar measure on the group.
A measure that's invariant under the group F.
There is a unique left invariant measure which is invariant under the left action of the group onto itself. So which means if you take a set and you assign a measure to this set and you take the left translates of this set, then it has the same measure, and you normalize it to be 1. So then you don't write this 1 over G there. So it's always a little bit, if you do both cases in once, you have to decide which one you write. So I write it in this lecture as being sums for finite groups, and for compact Lie groups we take integrals with respect to the Haar measure. So Haar measure for compact Lie groups. Okay, so let me write down a lemma, which is Schur's lemma. Sure. If we have rho 1 tilde, I don't know why he started to write tildes for this. The two complex irreducible representations. And the definition of irreducible in the complex case is the same one as he has given in his lecture. In the complex case, there is one specific difference to the real case. irreducibility and absolute irreducibility is the same for complex representations. It's not the same for real representations, but it's the same for complex representations. And we need this on spaces. And let me write them Cn, Cm. Suppose f from Cn to Cm is linear, and we have that if I so row 1 acts here and row 2 acts here. So if I first take row 1 and then I act with f on it, then I end up in Cm, and so this could be the same thing as first going with f over here and then applying row 2 to it. So this, of course, with the tilde, and we assume that this is true, and here we have a little g in here, and we assume this is true for all g in our group G. And then f is 0 if row 1 tilde is not equivalent to row 2 tilde. I'm not. I think John has introduced the notion of equivalence, but it's I mean, row 1 tilde is equivalent to row 2 tilde if there exists a linear map A from linear such that row 1 tilde is A, row 2 tilde A inverse, and this is true for all G and G. And so the proof is very simple. If this condition is satisfied, then we look at the kernel of f. W is kernel of f, and it's a very short computation. If you start with an element in the kernel and you apply row 1 to it, then you by this you apply row 1 to it. No, sorry. If you start with an element in the kernel, you apply f to it and row 2 to it, then you are at 0. So row 1 of G has to map this element into the kernel as well, right? Okay.
Is G the same as, I mean, how row 2 tilde composed with F? What's the domain of row 2 tilde? It's G, right? But F is valued in Cm. So do you mean that?
So this is considered as being an equality of linear maps. So for each G, this is a linear map from Cn into itself, and this is a linear map from Cm to itself. For each G, this is a linear map. And so for when I write this as an equality, then I mean this is an equality for all G as a linear map. Okay? It's really important to think about these rows to be elements of this GL of Cn or Cm in this case. Okay, and so if x is in W, then f maps x to 0, and this is a linear map, and it keeps 0. So if x is in the kernel, I have 0 on the right hand side, so I have to have 0 on the left hand side. So this element has to map x into the kernel, and so rho 1 tilde of x, rho 1 tilde of g applied to x is in W for all g. And then W is invariant. And by irreducibility, we have, I had this irreducibility assumption, rho I tilde irreducible. This means W is 0 or W is the space Cn.
Why not write down that line which you spoke? Just the missing line in between lines 1 and 2 of your proof.
Here,
Yeah. Why not just write down F composed with rho 1 of G applied
F
to W?
composed with rho 1 of G applied to X is equal to rho 2 of G applied to F of X, and this is 0. That's, this implies that this is in W. So, of course, I assume that F is not, if F is not 0. If F is not 0, this case is excluded. If F is not identically 0, W is to be 0. And then I denote by R F of Cn in Cn. And now I do it the other way around. If I start with if I start with a y in R and I apply rho 2 tilde of G to y, then this is rho 2 tilde G applied to F of something, of U, and this is the same as F. This is rho 2 applied to rho 1 of G at of U, and this is of course in the range in R again, because R is I mean this is this is an element in the image of R, and so R is invariant, and this implies R is 0 or R is full space CM, and this implies I mean, if R is 0, we are again in the case where F is 0, so we are in this case, and this implies F is an isomorphism. And if F is an isomorphism, then of course this equation which is written here implies this equation which I have written. There's an equal sign missing, so this implies this equation here. And because then F is invertible, and we have this relation. And so we have this lemma that an equivariant linear map between two spaces implies that their representations, and non-zero equivariant linear map between two spaces implies that you have the same representation on both spaces. And this result has very important consequences, and so let me maybe write one of the consequences down. So we have the same situation again, and this is again a lemma which is due to Schur. We have rho 1 tilde, rho 2 tilde be two irreducible reps of G as before, and we have spaces on spaces Cn, Cm, and then we have any linear mapping F from Cn to Cm linear, and we do a construction which is very typical for this situation. We define a new map which I call eta, which is I wanted to write it as a sum 1 over G, and so we have rho 2 of G inverse F rho 1 of G tilde, and then we have I if rho 1 tilde and rho 2 tilde are not equivalent, then eta is 0. I mean, this is it's an easy computation that this is going to be equivariant from one space to the other. And so if the representations are not equivalent by the previous lemma, it has to be 0. I want to skip the computation that this is equivariant. I mean, you multiply from left and right, and basically you use the left invariance of the Haar measure, or if you do summations, you just change the summation index between and so this is not very deep.
So yeah, so this thing's a linear map from Cn to Cm.
Excuse me?
It's this object eta is a linear map.
It's a linear map from Cn to Cm, yes. This is obvious, I think.
Yeah.
And it's it is equivariant on top of it, and so by the previous lemma, it's 0 if these are not equivalent. And 2i, if they are equivalent, if rho 1 tilde is equivalent to rho 2 tilde, maybe I should make one more remark. For equivalence, it's a necessary condition that n is equal to m, but of course you can have inequivalent representations in the same dimension. I just wanted to point this out. So, I mean, Schur would never write this with Cn and Cm. He writes some vector spaces and finite dimensional, and then this doesn't matter whether you have equal dimension or not. But here in this notation, it looks a little bit as if the dimension plays an important role, and I just want to make sure this is not only a question of dimension, it is really a question on the representation.
Always on the complex.
Excuse me?
Always on the complex.
So yeah.
Complex field is
The complex field is needed in two points. One of them we will use right away is that irreducible representations are absolutely irreducible. That this is the same thing in complex field, and in one of these arguments, which I did not really write down, you need an eigenvalue for a linear map, and for this, which is in the field, and in over R, this would not necessarily be true. And since I did not put down this argument, this cannot be seen. But okay. But this is of course important. If rho 1 and rho 2 are equivalent, then eta is equal to C times the identity on Cn, and C is a complex number. And here I use the fact that this is equivariant by construction, and it's these are irreducible, which means they are absolutely irreducible because this is a complex field, and by absolute irreducibility, this is a multiple of the identity. So I use something which we have not precisely shown, but I think this is not too bad. And in this case, we can even compute C. C is the trace of F divided by the dimension. Of course, in this case, we have n is equal to m, and so it does not matter whether I write down n or n. And the proof follows from what we had written down before, and this is a fairly straightforward proof. But I would like to point out that here we have a formula where we have written this is the identity on Cn, and if I write down matrices for this representation, this implies a relation on these matrix elements, which I multiply certain elements here, and this implies a relation for these matrix elements, which I will not write out, but you have a sum over Rij, Rj, I, and you add over all elements in G, and then you get something like delta n, delta Ij. This is a but I don't want to write this out. Okay. So this leads us to the next point. If we have a representation on Cn, then I can choose a basis. Basis in Cn. Of course, we know that there is no canonical basis. I can choose whatever basis I like to, and then I get a matrix. Then rho tilde has the form of a matrix, Rij matrix. Ij. Maybe let me write it. Rij. And here I run over Ij, whatever the best notation is. So I can write this in coordinates where each Rij is now a function of G. So Rij of G is a function of G. And I call such a function is called a representative function. So if I would ask it the other way around, what is a representative function? You get one if you find a basis, so that this is a matrix element with respect to this basis. I mean, given rho tilde or the equivalence type of rho tilde, it might be difficult to really find these functions. I mean, if you really want to do it, this can be very difficult. But it's an abstract definition. Whenever you find a basis such as that a function is a function in one of these matrix functions, matrix elements functions, then you call it a representative function.
Question.
Yes?
About the Schur's lemma.
Yes?
Is it possible to invert it? Because I've seen it many times in physical textbooks that they say if you want to prove that a representation is irreducible,
Mhm.
then you prove that if you assume there is an equivariant map,
Mhm.
so there is
Yeah.
these commutes with some f or eta,
Mhm.
and if the only possibility is that eta is proportional to the density, then rho is irreducible. So
Yes.
this is an argument that it is usually
Yes, but I mean, you see, the answer to this is you have in what we had last time, you have irreducible representation and you have absolutely irreducible representation. And if a representation is absolutely irreducible, then this is always true. This is or even true over R. And this is if the only if something commutes with all if a linear map commutes with all rho tilde of G, then it's a multiple of the identity. This implies irreducibility, but this is true only over C. So this direction follows for fields C or R, but this direction is only true over C. So you can check this irreducibility by checking absolute irreducibility, but this is always possible. But usually it's much easier to check the invariance or the non-existence of invariant subspaces. This is easier to check than to check that all linear maps commute with which commute with this group action are proportional to the identity. So for
Maybe it has to do with what I think John mentioned briefly last time, that if you have a reducible representation, then it means that you can put all the matrices in a block decomposition.
Mhm.
And therefore, in that case, you can see, like with the naked eye, that there are matrices that commute with that which are not the identity, namely a multiple of the identity in one block and a different multiple of the identity in the other block. So if you have this block decomposition, then it should never will fail.
yes, sure, yeah. Sure. Okay. So we have the notion of a representative function, and let me write down two more lemmata, which I don't want to prove, but which are some interpretations of what we have seen before. So we have this lemma. So maybe I don't have notes for what I'm saying today, but you find this all in more or less I write it down in the book I have written with Pascal. So it's in there, and our presentations there follows very closely. I should mention this, of course, very closely. Very nice book, which is this book by Sarah, Linear Representations of Finite Groups. So this is the fundamental book for all what I'm saying here. Let rho 1 tilde, rho 2 tilde be two complex irreducible representations of G as before, and we have mu1 ij and mu2 ij as sets of representative functions. So if then it follows if rho 1 tilde not equivalent to rho 2 tilde, I write this in short notation, not equivalent, then the sum over G, 1 over G, mu I2 J2 G inverse and here I have a 2, and here I have J1, I1, 1 is equal to 0. And if they are equivalent, 2i rho 1 tilde equivalent to rho 2 tilde, and of course this means dimensions are equal, then we have our summation over G in G 1 over G mu J2 mu I2 J2 2 G inverse mu J1 I1 G is equal. So this so you fix I1 and I2, and you as this is somehow this is one. Look at this. What to do? This is equal to 1 over n delta I2 I1 and delta J1 J2. Of course, here's the order. On this side, the order doesn't play a role. And this is a direct consequence of what we had before. And this implies the following theorem. If chi is a character of an irreducible representation, then the scalar product chi with itself, which is, so to speak, the norm square of chi, considered as a function in L2 of G, then this is equal to 1. And if chi prime are not equivalent, I mean, are characters of representations which are not equivalent, to be more precise, then the scalar product of chi and chi prime is 0. And this follows directly from what we have seen before. And for a finite group, G finite, L2 of G is finite dimensional, and this implies the number of irreducible representations is finite. Because the number of characters which with these properties, I mean, of course I look at linear independent characters which are with these properties, is a finite number.
So what's that argument again? Why it's finite?
I mean, you look at this is a finite dimensional space, and you look at the basis, unit basis of characters of length 1, length 1, and this is a finite set.
Oh, I see what you mean. It's,
Yeah.
it's finite because it's a basis.
Yeah. So if two of them are inequivalent, they are orthogonal to each other, and so yeah.
Reiner, I'm a little confused about what's going on in your lemma. So in the so rho 1 tilde and rho 2 tilde can be acting on spaces of different dimensions, Cn, Cm.
Yes.
So when you construct a representative function, you need a basis, right? So I mean, so there could be completely different bases, one completely different bases for
Yeah.
for the muse.
And matrices can be different sizes.
And these formulas are still valid. You knock together those are just two elements out of these matrices.
Yeah,
Once
but
you
there's no
fix the
summation.
basis.
Yeah.
And there's no summation implied. It's just head-to-head, just two.
So Mason's theorem. I mean, you pick any entry from one of the matrices, any entry from the other matrix, and you
Yes.
multiply them together, and you average over the group.
The number of group elements is of course the same. I mean, so you say I mean, if you have a finite group, you have the same length of these functions, so to speak. I mean, you consider it as a vector over the group, and you take the scalar product between these vectors. So this is not.
Of course, they are not evaluated on the same element.
They are.
One is on G and
Sorry, here.
minus 1.
Yeah,
This is
yeah.
essential.
Yeah, thank you. But I forgot to write G here. Yeah, okay. So now we come to something which I consider to be one of the beautiful results of the theory. Let's see. I don't know whether I should. But this I should tell you here. So we have the following theorem. Row complex representation of T on Cn. And we assume that Cn is a direct sum of Wi, and Wi are invariant subspaces. And so for each Wi, I have a character chi I, right? I restrict. I mean, I look at this. It's this row which acts on Wi, and so I have a character which is with respect to this Wi. Wi is a finite dimensional subspace, and so I have a character on this, and I call this chi I. And we assume chi I are irreducible. Then then I have another character, chi 0, let chi 0 be a character of an irreducible representation, and then I look at the following. I look at the scalar product chi, which is with the character to chi tilde, chi 0. And then if this is non-zero, then chi 0 is among these chi I. And the scalar product here gives me the number of times chi 0 appears in this list. I mean, so I have a list of irreducible representations which add up to Cn. I take one irreducible representation which might be among those or not. The scalar product gives me the information whether chi 0 is in this list. And the number here gives me the multiplicity of chi I in this list. So
What's chi itself in that?
chi is a representation of rho tilde.
Oh, the full thing.
Yeah. And so what I have is chi is the sum over I, so proof is the sum of chi I, and I look at the scalar product chi 0 is sum over I, chi 0, and this is non-zero if chi I is equivalent to chi 0 and 0 otherwise. So this okay, and this is the proof. Now let's make a little jump. We write f of GC is a free complex vector space over C. Over C. Okay. And so we consider the elements of G to be a basis for this vector space. So let EH be a basis. And then I look at a representation on this space, rho of G applied to EH is the same as EGH. So for each element in G, I have a basis element of the vector space, and my group acts on this by just moving this vector element, this basis element to another one, which I get by multiplying this H with G. Okay? This is a representation of G on this vector space, and this is called the regular representation. Regular representation of G, and it has the following property, and its character is chi G. So chi G of the identity element of G. This is identity in G is of course the dimension of this vector space. I mean, the identity element leaves everything fixed, because if you multiply EH, if you act on EH with 1, you multiply H by 1, which is H, so this is the identity element, and so the trace of the identity element is the dimension of the space. And so this is the order of G. And if you take any other element, if you look at chi G at an element lowercase g, and G is not the identity element, then this is 0. Why is it 0? This is if you multiply EH with G, you have EGH, and you have no diagonal entries. If you write this as a matrix, you have no diagonal entries. All the entries are off diagonal, and so the trace is 0. So this character is 1 at the identity and 0 everywhere else. This is a very important observation. You will see in a little moment why.
Where's the free
So now we take chi. Let chi be an irreducible representation of G. And now let's compute the inner product between chi G and chi. So this is a number of elements, one of the number of elements in G in G, chi G of G times chi of G inverse. Now, this gives a contribution if G is the identity, and otherwise it's 0. So we have just one non-trivial term here, and this is then 1 over the order of G, chi G at 1 times chi at 1. Because G inverse of 1 is also 1. So this is G over G. So this is chi of 1, and this is the dimension of rho. I mean, the dimension of the representation, of the irreducible representation. So in the regular representation, each irreducible representation appears with a number of times of its own dimension. So, as a consequence, we have the following non-obvious formula. So we have finitely many irreducible representations of a finite group. So corollary, let rho 1 tilde to rho r tilde be the irreducible representations of G. Now I can write down a complete list. There are finitely many. There's a complete list, and of dimensions di. Then the following is true. I is 1 to r, di squared is equal to the order of G. So if you square the dimension of the irreducible representation, add them up, you get the order of G. So let proof chi I character of rho I tilde then we know chi of G is the sum I is 1 to r. This is a list of all irreducible representations. So I can write this as a sum of all these characters, and each occurs with a number of its own dimension. So we have this formula: chi of G is di chi I, summation of I. Then we have the order of G is 1 over G chi G squared of 1. This was the order of G. Chi of G at 1 is the order of G, is squared over this 1. And this is the scalar product of chi G with chi G. And therefore we have G is equal phi g. Phi g is equal to phi g. Yeah, let me put in this here.
What's the dimension of a representation? What's di?
So if you have an irreducible representation,
Yeah,
there is an n associated with it.
yeah.
It can only be if you have. I mean, you could use the same representation as part of others, but if you have a representation, there's a dimension associated with this.
It's value in G, L, N.
It's a dimension of a matrix.
I know, but which one? I mean,
I-
all of those are evaluated in GLM.
So I have rho from G to GL and C. So this is the dimension of this rho.
Are those different for each of those then? Okay.
They could be different. They could be could be the same. But if
That's the end you mean then?
that's the end which I mean.
Okay, all right.
I mean, a representation has a dimension, and among those, I mean, if you start with a group, you don't know in which dimensions it will have irreducible representations. For example, take the symmetry group of the icosahedron.
Yeah.
Okay, you expect that you have a three-dimensional representation because you can see how it acts in 3 dimensions. But what other representations would you have? So this theorem will tell us that the number of elements in the icosahedral group, which is 60, is the sum of the squares of the irreducible representation of this group. And if you do the computation, it turns out you have 1 of dimension 1, you have 2 of dimension 3, which makes 1 squared plus 3 squared plus 3 squared, which is 19 now. Now we need 41 left, and 41 is fortunately 25 plus 16, which are square numbers. So we have it. So that's not a proof yet, but this is an indication. We have dimensions 1, 3, 3, 4, and 5.
But is this unique? Or
No, of course
Composition?
I could write 60 as 1 squared plus 1 squared plus 1 squared plus 1 squared 60 times, and this would also
Exactly.
be 60. This is not a proof. It's not a proof. It's an indication. But I can write down the representation. But I mean, this gives you an idea what is possible,
Direction to-
and then you can look for it. And if you think you find them otherwise, it's still a nice formula.
Yeah.
So we wanted to. So we have this here. For each of them, I write this sum here. So I have summation over I, di chi I, summation over I, di chi I, and this is summation over I, di squared. I mean, yeah, I should write di times dj times delta ij, and so this is the same thing as this here. And so this is how the formula comes into existence. And
And to make this useful, you like to do it so that the DI are as large as irreducible as large as possible.
there is only one set. I mean, given the group, there is one set of such dimensions. There's no choice.
I see.
This is a precise. I mean, if I take the icosahedral group, I find these numbers, and that's it. There are no others. This is a complete list.
If you want to get irreducible, then you have just the one. Right?
Explain?
Representation irreducible.
Yes.
Then you have one, but it's not irreducible, you can have three.
If a representation is not irreducible, you can decompose it in irreducible pieces, and let's say, to speak, the atoms which build the representations are these which are written here. Maybe let me do 2 more things. One thing is a very little formula which is extremely useful, which is a consequence of things we have seen here. And a second as an example, which is in the notes by John, which I wanted to just to write down so that one can see, and you can read it over again. So the formula which I wanted to show you is the following: I have a group G, and I have a subgroup H. If I have a subgroup H, and I have if rho is a representation of G, rho tilde, I can, with character chi, I omit the rho tilde in the subscript here, so I have a character which is a function on G. And of course, I can do the restriction of chi to H. So I have a new function which is just lives on H. This is the old function, but it's restricted to H. Now I can do the following. For each group, if I have any group, K, I define a map rho trivial from K to GL 1C, where rho trivial of K, little k in uppercase K, is equal to 1. This is a representation which maps every element onto the 1 in C, which is a matrix, a 1 by 1 matrix, a linear map on C. So this is a trivial representation. The trivial representation has a trivial character, which is for each element 1. So what I can do, I can ask how many times in this restriction you find the trivial character of H. So I ask for the number of times trivial character of H appears in chi restricted to H. Of course, this is chi restricted to H, scalar product, with trivial character of H. Let me write it H here, so I should denote the group somewhere. Trivial character of K, trivial character of K. So we look at this here. This is nothing else than the summation over the elements in H of the character, of the original character, chi, of H. I mean, because the scalar product with the trivial character just multiplies H1 with each entry, so I just add this here. And so this is this part of the formula, but what is it? The number of times the trivial representation occurs in H. It occurs in chi. It means the dimension of the fixed point subspace of H. Because for each dimension, I get one of the fixed point subspace. I get one trivial representation. If you have an element fixed on the H on this line, spanned by this element, this acts trivially, and so the number of independent trivial representations, so to speak, which I can get, is just the dimension of H. So this dimension of fixed H. So this is equal to the dimension of fixed H. And so this is called the trace formula. And it gives you a very easy way of computing fixed point dimensions of subgroups. Okay, so this is the theoretic part, and now let's do one example which we had already discussed this afternoon. Of course, maybe it would be interesting to do more difficult examples, but let's do a very simple example. Let me start with one remark. If you have an abelian group, then all irreducible representations over C are one-dimensional. For any abelian group, all the irreducible representations are one-dimensional, which is not true over R. Over R, irreducible representations can be one- or two-dimensional. The easiest example is if you take rotations by 2 pi over n in R2. This is a irreducible representation on R2 if n is not 1 or maybe 2. Then it's a true rotation of this, and this has no invariant subspace, no non-trivial invariant subspace. But it has a two-dimensional irreducible representation. But you see, since this group is abelian, it commutes with all the matrices which are in the image of rho of this group. So this is not absolutely irreducible. By its very nature, it's not absolutely irreducible because it commutes with itself. And therefore, there you see what is the difference between real and complex representations. In the complex case, such things would not happen, because in the complex case, the rotation is one-dimensional. Right? You rotate the complex plane, and this is a one-dimensional representation of this group. And so you can see how these things fit together. But now let's do this example. We write D2 for the following group. It has a 1, it has an element A, B, and C, and we require A squared is B squared is C squared is 1, and AB is C. And the others is similar. And then this is abelian, and therefore all the representations are one-dimensional. And I write down the complete character table. We have D2, so 1, A, B, C, and since all the representations are one-dimensional, we need 4 of them, because this is 4 elements. 4 times 1 is 4. So the first representation sends everything to 1. This is a trivial one. Then I have a representation where I send, so I can write down ones here. This is trivial. Then I have here I write a -1, and here I write a 1, and then I have to write the product of this, which is a -1. And let me write a 1 here and a -1 here. Gives me a -1 here, and if I have a -1 and a -1 here, I get a 1 here. So this is rho tilde trivial. This is rho tilde 1, rho tilde 2. I keep the tildes. And or the character, in fact, the character of this. And now, of course, we all know a two-dimensional representation of this in rho without tilde. It's from G to GL2R, which I write 1, 1 for the one element. 1 goes to here, A goes to 1, -1, B goes to -1, 1, and C goes to -1, -1. So if I write, here's a character of rho of my new representation, I get a 2 here, I get a 0 here, I get a 0 here and I get a -2 here. So for example, now I can see how often is the trivial representation contained in there. The scalar product of rho with rho trivial tilde, trivial has no tilde, is 1/4. And now I just add these numbers multiplied in the same column. So 2 with 1 multiplied, 0, 0 does not give any contribution. This gives 1 times -2 is 0, is 0. So the trivial representation is not contained in this one. But if I...
The last row is a character, isn't it?
Excuse me?
The last row you've written
Yeah.
is a character
Of the representation I've written up there.
yeah, but the character, not row itself.
Yeah, but I always have written the character. This is a character corresponding to this representation. But of course, you're right. If I would go into a more fancy notation, I would forget about the representations and I would just write down characters and forget that I have representations. But I thought we are still on coming from representations and keeping this and so.
Excuse me, and the geometric meaning of the fact that there is no trivial representation is that there is no vector.
There is no vector fixed under this group.
Okay. So if you apply these matrices to any AB vector, so two-dimensional vector,
Yeah, I mean, you see, if you take a vector which is non-trivial, it has at least one non-trivial entry, and so this element will move it if it's the second one is non-trivial, and this will move it if the first one is non-trivial, and so none is fixed under this group. So this is the geometric meaning of this thing here, but we can, for example, ask whether this is contained in this one. So we take rho with rho 1 tilde, and so we have 1/4, and so we have a 2 here, we have a 0 here, and we have a 2 here, which is 4. So this is contained once. So this representation, rho 1 tilde, is contained once, and if we take rho 2 tilde, we have the same thing. 2, 0, 0, 2 is also 1. So this, my rho at the end is the sum of rho 1 tilde, direct sum rho 2 tilde. So, and of course you see the block diagonal contributions directly from what I've written.
So where do we see the sum of squares formula?
Excuse me?
The sum of squares formula.
Yes?
How do we see this? One
squared plus 1 squared plus 1 squared plus 1 squared is 4.
Okay, because the only reducible ones are one-dimensional.
Yeah, it's abelian. It's abelian,
Yeah,
yeah.
of course, sorry.
Yeah, sure. You want to see one more application of this formula? So let's final step. We look at the group D3, which is a symmetry group of a triangle, equilateral triangle in R2, and it has 6 elements. So 6 can be written as a sum of squares in one obvious manner: 1 plus 1 plus 4. So this is a standard representation. Now let's do it on C2 or in complex Y, because of course this counting is only valid over the complex numbers. So one one representation is obviously high trivial, or one character, row trivial. Oh, this gives a 1 here. And then we have this subgroup has a subgroup. P3 has a subgroup Z3, the rotation subgroup. This is a normal subgroup. So one homomorphism is from D3 mod Z3 into the 1 minus 1. I mean, this is a two-element group, and this is two elements, so I have an obvious mapping. And so this is my second one, which is also one-dimensional. And in fact, these are also real representations. And then we have a group representation on you see, there is no representation on C, because of course I can realize the rotation on C, but then I need a reflection, and the complex conjugation is not a complex linear map. So this is not a representation on C, so I have to do it on C2, and so I rotate on C2, and I do the reflection by exchanging the two elements, and then this is a two-dimensional representation. Yeah. So I have Z1, Z2, and I do the rotation in a diagonal form, and I have Z1 exchanges Z2 for the reflection part of my group, and this is a reducible representation, and so I have a two-dimensional one. And let's go to this. Thank you very much.
Thank you.
Any questions?
Because we've had all the questions as we go along. It really is it's amazing theory, amazing that it all works.
Yeah.
So this says if you've got a group of 8 elements,
Yes.
you can only have representations of dimension 2. So things like that.
No. If I have a group with 8 elements,
Oh, sorry, except for one. No, you can have
Also-
1, 1, 1.
yeah,
The
yeah.
maximum dimension would be 2.
The maximum complex dimension would be 2, yes.
Except for, yeah. And 9 as well.
Yes. You always have the trivial representation,
That.
so you have always to take one off
Yeah.
for the trivial representation, and then
Maybe it's a naive question, but the reason why you haven't chosen to analyze 1 plus 1 plus 1 6 times instead of, so why did you immediately choose the 4?
because I knew this before. I checked it last time.
Also, having 1 plus 1 plus 1 plus 1 would mean a billion group.
Well,
Isn't it?
billions have a one-dimensional representation. I
Yeah.
don't know if the other way
The
around
other way around, that probably is also true.
What if your group isn't?
The other way around is probably also true, yes. Of course, I mean, if all the representations are one-dimensional, then each image is a billion. Rho of G is in a billion group because subgroups of C are a billion, and so if you
These are numbers.
yeah, then it's also true. Yeah.
Yeah, because for any non-abelian group, you can always find a representation which is non-abelian.
Mm-hmm.
Is there any theorems that say you can always know, just have one representation which is non-abelian and the rest can be really, in my opinion, you know, is there any kind of splitting it up like that? Can you take out the non-abelian bit into one representation?
I mean, you have something which is called the commutator subgroup, and of course, if you look at G mod its commutator subgroup, then the rest is abelian, and so. But of course, the commutator subgroup could be very large and could have many representations itself. So it's not. I think there's no real way of saying it. But maybe one remark. If you do bifurcation theory, and if you want to find, for example, fixed point spaces, then we have seen this can be done by character theory, and so you can let's say you give a group, you can find its representation, its irreducible representation by character theory, and you can find all its fixed point spaces in dimensions, and you can so to speak create a full partial ordered set of isotropy subgroups only by character theory. So this can be done in a very efficient way. There is a computer algebra language which is called GAP. I almost forgot the commercial here. GAP is, you can get it on the net for free. So this is a commercial for a free product. With this, you can do all the analysis you want to do on finite groups in milliseconds. I thought for a very short time to bring my computer and show you how this works. But if you want to see it with GAP working on, I can show you plenty of examples, and you can see how efficient it is. It takes milliseconds for reasonable groups. So if you take a group of, let's say, 1,000 elements, it's still in the I compute many more information rather than the isotropy subgroups in its dimension of the fixed point space. I also compute how many times an orbit of one type would land in the isotropy group of some other type. So this is a much more refined information, and this takes a few seconds on my computer.
It gives you dimensions.
Excuse me?
It gives you dimensions of the isotropy.
Yes, the dimension of the fixed point spaces.
Yeah. So there is still some work to be done.
You see, my dream is to write a program which uses characters only, which produces also bifurcation diagrams. But I'm not yet there.
Not people out of job.
I don't think it's possible.
That's idea of mathematics.
Okay.
Thanks, Reiner.